Hello, Sawasdee, my student. This clip is going to be about chapter 6 of the theory of structure. We are going to talking about the inference line diagram of the beam mostly. Thinking about the picture in front of you, there is the car, right? The car is a moving load. The car is not just static to be any pace and then going to be there for a long time. The car move. When the car move and then if you have the beam supporting the car, you can imagine that the reaction that occur in the support of the beam always change with the position of the car. And then the change is going to be a kind of a diagram, and we call it inference line diagram. Inference line diagram can be inference line diagram for the reaction. It can be the inference line diagram for the shear force. And also we have the inference line diagram for the moment. Okay, so for this chapter, the first learning objective is to understand and be able to draw inference line diagram of beams and girder. Okay, and then we will use this learning objective 1 to apply to the learning objective 2 to understand and be able to determine the loading pattern. So we apply the learning objective 1 to find the loading pattern, okay, from the inference line diagram that will produce maximum reaction, maximum shear force, and maximum moment at a given point of the beam, and can use the obtained result to draw the shear diagram and moment diagram. Usually the learning objective 1 and learning objective 2, they are linked to each other. Anyway, in the examination, I will try to separate them so that if you get a wrong answer for the chapter 1, you will still be able to do the chapter 2. Okay, and the third one, to understand and be able to determine the absolute maximum shear and absolute maximum moment. Okay, you know the word absolute, right? The absolute is the maximum of the maximum. Okay, and there is a problem such as there is a girder of a bridge, and then you have the 18-wheeler. On the learning objective 3, you got to put the 18-wheeler to some point in the girder to produce the maximum, absolute maximum shear. Also, you put in another position to obtain the absolute maximum moment. That's going to be another examination problem. The benefit of learning the inference line of statically determinate beam and girder is to use the result to design the structure subjected to the moving load, such as bridge, okay, such as crane. Okay, let's see. This is an example of a bridge that's link between the pier from the left and to the right. Okay, you can see the car is here. Okay, it's always move from here to somewhere else. When is it here? The reaction over here is small, right? The reaction here is large. However, when it's moved to this position, the force here is going to be large and the force here going to be small. So the change along this movement of the load and consider for an effect such as reaction as a point. We call it inference line diagram, and this can be used to design this kind of beam on the interchange. Okay, let us come back to the concept of shear and moment diagram. And as you may see, we draw this diagram to get the Vmax and to get the Mmax. This diagram though bases on what? Based on the beam is subjected to the fixed load. The load here is fixed, such as this is 10 kilonewton, and this is, for example, like 3 meter, and this is 9 meter, and the load gonna be here while you draw the shear diagram and moment diagram. Okay, and then the fixed load come from what? The fixed loads come from the building code and the design code to get the life load, such as it is beam for the office or beam the kindergarten. The load, life load is going to different from the beam in the university building, right? Anyway, if you may recall, and when you get the Mmax and Vmax, you can design the section of the beam as it shows here. The section may be rectangular or structural steel section, those kind of thing. And for the inference line diagram, the beam is acted by a moving load, okay, along the beam length. The objective of this diagram first is find the reaction or shear or moment at a given point on a beam, such as if you have a simple beam, you like to determine the reaction at point A. Okay, this is going to be the R sub A. And what is the load is going to move? Okay, usually we assign the 1.0 point load to represent the x magnitude of force. Okay, if you set 1, so you can multiply 1 with anything when you have you are giving force. So the inverse diagram produced by putting the force at A first, and then you determine the what? The R sub A. For example, here you just put it there, and then this is 1. You take the moment here. This is going to be R sub A. This is B. Summation moment V equal to 0. So R sub A equal to 1. And then you move this one to this one. So the second, the free body diagram gonna be something like this. Okay, and you take the moment at B again, summation with B again, you get what? You get R sub A, R sub A time what? 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, is equal to, this is 1 time 18. So your R sub A gonna be 0.9. So you get this 0.9. And then you move again to this. You do the same thing. You just draw the free body diagram and find R sub A, and the force is here. Now it's gonna be 16 meter. Takes moment here. You got 20 R sub A equal to 16 times 1, and then you get R sub A equal to 0.8. Okay, you know this is going to be total of 16 meter. It's going to have this. When you move this, it's going to be 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1. And then when load arrive at B, all the force transfer to B, there is no R sub A. And the change in this inference line, okay, is called the inference line diagram. Next, you may see the inference line diagram have all positive value. We will find the loading pattern. Usually, the loading pattern is up on the live load. For dead load, okay, is always, okay, B, always B, along the beam length, is always along the beam length, because dead load is usually in the form of cell weight, okay, but the problem is the live load can change anything, okay. It can be short if it's possible, or it may be very long, such as when you have the traffic jam, okay, traffic may jam or the whole bridge, or it may jam only on the half bridge, okay. And then what we should put the loading pattern, okay, to use them to compute the maximum reaction. For this one, you can see this is going to be on the area here, because all the influence there is positive, so you just put in the positive. And next, you can do the same thing, but I'm not show you here. You just move the loading, okay. If it is here, we're going to find the shear of 1 okay, the shear on this section, when 1 is here, the shear on this section is 0. When the 1 unit force move, the shear at this section change to minus 0.1, and it on the left of section 1, that is going to be minus 0.2. And when it moves to the right, okay, to the right, you got positive 0.8, and then it will follow the 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1, and then when the force acts to the roller B, there is no shear at the section 1, and then you get this inference line diagram for what? For the shear at section 1. There is minus and plus, okay. The minus, that means inference is negative. The plus means inference is positive. So when you put the force, you see the plus larger than minus. So the force gonna put only in the plus area to get the positive influence to use to compute the shear at section 1. Okay. And next, bending moment. You do the same thing. You move the 1 unit load from A to B. Okay. Every step you do the free body diagram, compute your moment. Okay. And then you put the graph. If the force at A, again, the force applied directly to the support, so there is no moment at section 1. And then if you move it to this position, the moment at this section 1 will change from 0 to 1.6, okay. And then you move it to the left of section 1, you get 3.2. You move it to the right, and then again you get it for 3.2. And then you move further, you get the coordinate of each point to draw the inference line diagram of section 1. And again, if the force is SB, there is no moment at section 1. Okay, to get this. And this time the influence of the bending moment is positive. So the loading pattern is like this. Now you can see that the loading pattern can change with the change of influence line diagram, such as the loading pattern for this bending moment and the loading pattern from the shear force at the same section 1-1. They are different. Okay, the example of application. If you consider this crane have the moving load here, okay, the beam of this crane is subjected to moving load. We analyze this beam and draw the influence line diagram of the beam to find the load pattern that produces the maximum reaction, maximum transfer force, maximum bending moment at some specific point. For example, the reaction R sub A, or the shear, sorry, this is not A is already there. Let's put this one is R sub B. Okay, let's say this one is R sub B. Okay, or this one going to be V sub A, M sub A. If this point is C, you will find for the R sub C. Okay, how do we put the loading to get the maximum of what reaction, maximum shear force, maximum bending moment? Okay, and then we can use that to design the beam properly and safely. So this is the importance of the influence line diagram for this crane. Also the bridge, you know, the bridge, the car can move, okay, along the bridge. So the weight that applied to the structure will change with the position of the car and how we put it and make the shear to be absolute maximum and absolute maximum, yeah, and also the moment being the absolute maximum. That will be used to design the structure safely. Okay, let us start by drawing the inference line diagram. We will have start with the method 1. In method 1, you will to move the force step by step. Okay, and then we compute the reaction for each loading step, and then we move another step and compute the reaction or the shear and the moment for the second step, and then we move step by step like that and then do the same thing. The method is going to be very straightforward but very time consuming. Let us consider this example. Okay, we will draw the influence line diagram of R sub A, the reaction here R sub A, and R sub B here. Okay, and by the concept of this, we're going to move the load step by step and compute the R sub A and R sub B. First, we put the unit load. It's always unit load here, unit load นะครับ at the coordinate 0 meter at A, and take the moment about B. We can see that this one R sub A gonna be 1.0. Okay, and if you summation f sub y equal to 0, you get R sub B equal to 0. Okay, that's the first step. And second, we move it here to coordinate of 2.0. So this time, if you take moment at B, you will have R sub A times 20, and this 1.0 unit gonna time the length here of 18. Okay, and then you have this one, and R sub A gonna be 0.9, and then if you use the summation f sub y equal to 0, you will get R sub A plus R sub B equal to 1. So the R sub B gonna be 0.1. you're going to use like this, move this, okay, and then now you have what? Take moment at B again, and this time R sub A time 20. This 1.0 unit gonna time what? Gonna time 16 meter, and then you get this, and R sub A gonna be 16 divided by 20, that is 0.8. And do the same thing, summation f sub y equal to 0. You got R sub B of 0.2. Okay, and then you do it again. Take the moment at what? As a B. Okay, and the R sub A times 20 and equal to this 1.0 gonna time what? Gonna time 14 meter. And then you got this one for 0.7. And you get the R sub B of 1 minus 0.7 is R sub B equal to 0.3. Okay, and do the same thing. Yeah, if you not ball it with this, R sub A gonna time 20. That's 1.0 gonna time what? Time this is gonna be 12 meter. And then you get R sub A of 0.6. And then you get R sub B of 1 minus 0.6 is going to be 0.4. Okay, you're doing it like this. Okay, continuously you can see the R sub A and R sub B have the relationship based on the summation of f sub y equal to 0. I mean the summation of R sub A and R sub B always 1. They are always 1 because it must be in equilibrium. And if you draw the graph, you're going to have the graph like this, as you have this graph of R sub A before, and for R sub B is like this. Okay, the same happens if you like to determine the inference line diagram of V11, I mean the shear force at the section, this section 11. Okay, and then the moment also at this section by using the same method. Okay, we use the free body diagram, determine the shear and the moment, and then we move the force, we draw the free body diagram, we determine shear and moments by using equation of equilibrium. Step will be like this: move the force to a new position, draw the shear diagram, and draw the free body diagram and use the equation of equilibrium to determine the shear force and to determine the bending moment. Okay, if you understand that, let us start by putting the unit load here, and you may see the R sub A gonna be 1.0. And if you cut, okay, the section, draw the free body diagram of that part, you may see the shear force here is gonna be V1-1 plus 1.0 equal to 1.0. So this one gonna be 0. Okay, and if you summation the moment, again, if you summation the moment at this section, you will get what? This M-11. You're going to pass 1 times 4, and it's going to be equal to 1 times 4. So all the shear and the moment is 0. And then if you move a little bit, 2.0 meter from A, and you may remember the reaction here, right? It's going to be what? It's going to be 0.9. So the free body diagram of that segment is going to be like this. And then you can draw the free body diagram and put this one to 1.0. So this time V1-1 plus 1 equal to 0.9. Okay, so you move V1-1 is equal to 0.9 minus 1. Okay, and then you get this for 0.1. is downward. Summation of f sub y equal to 0. So v1 dash 1, the pink, plus 1.0 equal to 0.9. So v1 dash 1 is equal to 0.9 minus 1, and then get this, right? And then you take moment here. Summation of the moment equal to 0. And then you get what? You get m1 dash 1 over here. And then this one gonna rotate in the same direction as the moment. So plus 1 times 2. And the 0.9 gonna rotate in the opposite direction. So you get 0.9 times 4. Okay, and then you get this n1 dash 1 equal to 0.9 times 4, and then minus 1 times 2. You get this is 1.6. Okay, and go further on the left of this. Why? Since the shear going to make the applied force going to make the shear, delta shear, the change in shear at that point significantly. That's why we got to put for the shear the applied force on the left and applied force on the right. Okay, again, you may remember this, what we have for the R sub A. This one is 1.9, going to be 0.8, right? That's going to be 0.8. And then the free body diagram going to be like this. The applied force is going to appear over here on the left of section 1.1. And then you do the same. You have what? You have the shear and moment, and you do the summation of the force equal to 0. And then you have v1 dash 1 plus 1, both of them downward, and then minus 0.9 and minus 0.8, okay, and equal to 0, and then you get it of minus 0.2. And then you do the same thing. Don't bother with it. Take the moment here. So the 1.0 produce no moment. So summation of moment equal to 0. Put this one is positive. So m sub 1.1 going to equal to 0.8 times the length of 4 times 4. So you got the moment of 3.2. And then you move it to the right. Okay, and the R is going to be the same. The R. Okay, the R is going to be 0.8. You go to the previous example. And then what you have, the free body diagram now. The 1.0 just gone away. And then you have the shear and the moment. You do the same thing. Summation of the force equal to 0. So v1 dash 1 downward is equal to 0.8. See, it's jumped from minus 2 to plus s. And then if you do summation of moment equal to 0, this time it's going to be very simple. The m-11 gonna be 0.8 times 4, and then you get the result v-11 and m-11 like this. And as you may see, this moment at this point are equal no matter the force, the applied force of one unit is on the left or on the right of the section 1.1. However, the shear have the change at this point in the total of 1.0. Previous slide we get v-11 of minus 0.2, and this one we have it for 0.8, or if you said this is previously when here is 0.2, and when it's moved here this is 0.8. So the total of force here is 1.0. Next, we just move it again, and if you remember, at this point we have the r sub a of 1, 0.9, 0.8. It's going to be 0.7. Okay, we're going to have 0.7 here, and then we didn't need to change the free body diagram. We just use the same free body diagram as before. Since this portion, you may use this portion, or you may use the other portion, you will get the same shear and moment, just different in the, not different, opposite in the direction. Okay, and when the force stay on the other side of the beam segment and you use this portion, you can compute easier because the 1.0 unit will not appear in our equation. Okay, and if you get that, we just cut this portion and draw the free body diagram, and the moment and shear like this. So this time is very simple. V-11 is going to be 0.7, and again, if you take moment here, M1-1 gonna be 0.7 time 4. Okay, that is gonna be 0.7, and 0.7 times 4 is 2.8. And then you move here. Now it's gonna be what? The reaction gonna be 1, 1, 0.9, 0.8, 0.7, 0.6. Okay, so 0.6, and free body diagram only on the same portion as before. Just consider only this portion. Okay, and then you have this. So the shear gonna be 0.6, and the moment gonna be what? Moment gonna be 0.6 times 4. Okay, and then you get this one for 2.4. Okay, if you do the same thing like this and you plot the result with respect to the coordinate x from 0 past 10 to 20, you will have r sub a, inference line for r sub a, inference line for r sub b, inference line for shear at section 1-1, inference line for the moment at that section. And putting all the number into this, you will get the shear diagram and moment diagram. And this shear diagram and moment diagram we have discussed on the start of this clips, right? Okay, this is kind of taking a lot of time to draw the shear diagram and moment diagram. So we move to the second method. Okay, the second method, when we put the 1.0 unit onto the beam. Now this time we put the position as x. That means if you put this one, you put this as x. And then we find the equation for the r sub a, we find the equation for r sub b. Okay, and then later you can find the equation for the shear force and the equation for the bending moment at a given point. Okay, and then do the same thing. This time you're gonna write the r sub a. Let's say you have a 1.0 here, and then you like to find r sub a. You take the moment about b, so r sub a gonna time 20, and then it's gonna move like this. This one gonna time what? Gonna time this distance, and this distance is gonna be 20 minus x. So this one 20 minus x is gonna rotate in the opposite direction. So you got this. And when you put into this, divide all of them by 20, you get 1 minus x over 20. Now you can plot for every x. If x equal to 0, this one is 1. Is x equal to, let's say, 18, this is 18. 18 divided by 20 is going to be 0.9. This is 0.1. Okay, you put it like that. It's going to be very simple. And then summation of f sub y equal to 0, r sub a plus r sub b equal to 1. And then you may have this one for what? 1 minus x divided by 20. This is r sub a plus r sub b and then equal to 1. Then your r sub b gonna be 1. And then you move this one from plus to minus, from minus to plus. Okay, and then you get this equation. Just cut this. Okay, plot the third, plot the required diagram by using the obtained equation. This is kind of straightforward and easy to apply, but it's not the fastest way yet. We're going to talking about the method 3 later. Okay, but the method 2 is kind of important because it's going to be the basics for the other method 3. Okay, so you need to understand it. The same thing as we did in the method 1. First, we will put the 1 unit force to a position on the beam, but this time we put the position of x. Then we draw the free body diagram of the beam, and then we use the equation of equilibrium to determine the equation for the reaction, for the shear force, for the bending moment. So first, let us find the equation of r sub a and r sub b. The same thing occurred there. We did before. Take moment at b, and then now we have r sub a. R sub a is here. It's gonna have L, and it's gonna rotate. What? It's gonna rotate in this counterclockwise direction. And then 1 must time L minus x, but this time it's gonna be in the opposite direction, so they are equal. And then just put r sub a equal to L over L minus x over L like this, and then you get 1 minus x over L. And then summation of f sub y equal to 0 as before. We have r sub a of what? Of 1 minus x over L, and then plus r sub b equal to 1. So r sub b is going to be 1 minus 1 plus x over L, and then you get this equation. Okay, and then you draw this. You got the diagram at a function like this. And I should mention one thing at point C. We separate the beam at point C into the distance A and the distance B, and A plus B equal to L. Okay, this is going to be the point C. At point C, the r sub A gonna be 1. R sub A gonna be 1 minus x equal to what? X is moved from here to here, so x equal to A. So it's gonna be A over L. And then if you put this as L minus A over L, and then L minus A, you have L here, you minus A, you will get this for the B. So it's gonna be over L. Okay, the value here is B over L, right? And then if you project it down here, and again you put the x equal to A here from this equation, so R sub B equal to A over L. Okay. Okay, and you also can see that the diagram that you get is the same as before if you set the L as before equal to 20, and then you will get this one top 1 minus x over 20, and this one gonna be x over 20, and if you plot the graph you will get the same graph as before. Okay, Okay, next we're going to find the equation for the V sub C and M sub C for this inference line diagram. And the concept, as you may notice before, when the force is in in some area, for example, if the force is is in this area, this means when the force is in this region, it's going to be as shown before. It's going to be as shown before that you supposed to use this portion of this free body diagram of this portion to compute the shear force and to compute the moment. Why? Because on the light blue section of this beam, the free body diagram going to have no unit load force, and the computation going to be easier. So in conclusion, we're going to use the BC to determine the equation of the shear for the unit load that's in the AC region. Okay, take it like this, and the free body diagram gonna be on this portion, and let me put this like blue, make it the same portion above there, and then we just take the we just draw the free body diagram. We get this R sub B equal to X over L. We got the shear V sub C and M sub C, and I should note something. When you cut the beam, okay, you got the beam on the left and on the right, so the moment and the shear on this side is like this. This is going to be positive sign convention that we use since we study the ending static, and this one going to be positive for the segment on the right hand side. So summation of f sub y equal to 0. You may see this one, if you do the summation of f sub y equal to 0, v sub c is up. Okay, v sub c is up. R sub b also up, equal to 0. So v sub b equal to minus r sub b. So what if you have this? So what you mean is, if you consider for this portion, so we have the r sub b like this, and then we have the v sub c equal to minus of r sub b. So that means we have the reverse of r sub b here, and then we have this for minus a over L, because this one is a over L. Okay, and next let me illustrate this for the same thing. Okay, and let me take a note here. That's going to be minus a over L, and then summation of f summation of moment at C equal to 0, and you may see easily m sub c is here, and r sub b gonna time b. So the next portion, what we have is the same moment, the same diagram, and this time we have the r sub b here, but the r sub b gonna time what? Gonna time b, and so this one is 0, this one's still 0. For this is a divided by L, so this one gonna be a divided by L time B. So it's going to be AB over L, and then you get the graph like this. Okay, that is the graph like this. Only this portion of 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 the diagram, and then you also get this one for AB over L, and you're supposed to note that the slope here is going to be B over L, because this is going to be B. Okay, and that's L. And next we move to the other part of this. Now we move our force into the C to B portion. So this time the force now move into this portion. Okay, and then we're going to use what? We're going to use the segment AC here. Okay, and AC here to draw the free body diagram, because this time the force move. Actually, choose this one. No, it's not correct. This one take out. This time force move to here. Okay, and then this is gonna be the X. Okay, and this is gonna be L minus X. This is the correct picture of this. Now the force move from segment AC to segment BC, CB, and now again we will use this portion, the yellow portion. We will use the yellow portion to draw the free body diagram and find the shear and moments at C. So the R sub A is going to be 1 minus x over L, as we know before. And when we just summation of f sub y equal to 0, summation of f sub y equal to 0, and then you get what? You get V sub C. V sub C, downward is positive, V sub C, minus R sub A equal to 0. So what it means is, if you have the diagram here this time, and your diagram will start from this until this, and what we have is the graph here. Okay, so you just copy this graph, because V sub C equal to R sub A, and then just put it over here, and then you got this for B over L. Before that you have this, and this is minus A over L. And I should note that the combination of this gonna be A over L plus B over L is gonna be L over L, and it's gonna be 1.0. And I also need to point out that the slope of these two lines gonna be the same. Okay, you can prove it easily. Okay, and if you do the summation of summation of moment about C is 0. Just take the moment here, and then you have this one for plus M sub C. M sub C gonna be what? M sub C gonna be R sub A times small a. So you got this. So now on this portion, okay, you got this, right? This is B over L. So you got to time with A. So this one again, AB over L. And then if you come here of 0, this is going to be 0 times A. So this is 0. And then you may have the graph like this. And also you have this one before. And I should note that the angle here in combination going to be 1.0. Okay, that's let me show you. We follow the PowerPoint that is have. Take this one out. If you not understand this, you should go back and do the revise or just rewatch it again. So this one is going to be the moment. Okay, this is B over L, this is AB over L, and finally you arrive at this important inference line diagram. Okay, we now recover from this. Let me try to focus what we have here. Okay, and this is the end of the example that we determine the function of the R sub A, reaction at A, reaction at B, R sub B, shear force at C, V sub C, and the moment at C is the M sub C. And then we arrive at this. There are some important things that I should mention for the R sub A. Okay, R sub A have value 1 here, and the value of R sub A just decrease, okay, until here is 0. For the R sub B, the value R sub B start from 0 and be 1.0 here. And if you can see, the equation R sub A is this one, and equation R sub B is this one, and you may have R sub A plus R sub B, okay, equal to what? Equal to 1 minus x over L and plus x over L, and you're going to get this one for 1.0, because the combination of the reaction always equal to the applied force of 1.0 there, okay, 1.0 there. And then when we come to the shear diagram, the shear diagram going to start 0 from here, and it's going to downward to minus A over L here. And since the force here is 1, so it's jump up to B over L. Okay, so the combination of this is going to be 1.0, and also they are in parallel, and the end of B is going to have 0 value. Okay, and for the moment, again, we have 0 moment here because it's a pin, and 0 moment here because it's a roller. And then at the C, we get the value of AB over L. And also we have the angle here of 1.0. Okay, I like you guys to at least remember or get used to with this diagram and values and equation and characteristics of the diagrams. Next is going to be the third method to draw the inference line diagram. Okay, based on the work of Muller and Bayes' law many years ago. They are trying to figure out how to draw the inference line diagram of the reaction, inference line diagram of the shear force, and inference line diagram of the bending moment effectively. So there is word here, but I like to put it in my own word for this definition. If you like to draw the inference line diagram, okay, of a function at a given point, okay, you take that function out of the beam. For example, if you like to draw the inference line of reaction, you take the resistance of a reaction out of the beam, and then you put the reaction, okay, you put the reaction acting on the beam, and then the shape of the beam is going to be the inference line of that function. Okay, let's show you like this. Okay, but before I show you, one more thing, the beam here is always rigid beam. So on the inference line of statically determinate structure going to be a straight line. No, series of straight lines. And then let's see. If you like to draw the inference line diagram of the reaction A sub y. So you're going to change by what? By eliminate the resistance of the A sub y out of the pin A. By eliminate that mean you're gonna change the pin support A to be the roller guide like this. So it has no resistance to the A sub y. And then you put the reaction A sub y and move this one up. Move this one up for 1.0 unit. And then the shape of this beam gonna change to be like this, the dashed blue line. This dashed blue line is the shape of the inference line of A sub y. Okay, let me do it again. If we like to draw the inference line of reaction of R sub B, so this one going to be the pin again. I release the resistance of B sub y out. That means I take this reaction out and then I put the R sub B here and move this one up for 1.0 unit. And then what happened is you got the inference line diagram of R sub B here. Okay? Okay. And then for the shear. When you draw the inference line diagram of shear force V sub C, you're going to eliminate the ability of resisting shear force here. We eliminate it because we're going to try to move it. Okay, then we apply the V sub C. Okay, all of them are positive V sub C. And then when you move this one gonna be the rotating point. You're gonna have the shape like this. And this one also, you're going to have the shape like this. And since it has the free end, so it's going to extend to be like this. Okay, this is going to be the inference line diagram of V sub C. Change point C to be the roller guides. Okay, that means eliminate the resistance of shear force out, and then put the shear force into the roller, positive shear force, and then the shape of the beam change, and then that is going to be the inference line of shear force C. And it is important to note again that the summation of this difference going to be 1, and this line going to be in parallel. Okay, and the value of on the left hand side going to be minus A over L, and on the right hand side going to be plus, let's see, this is going to be plus B over L. This is going to be minus and parallel. Okay, then for the bending moment at C, the first one you got to what? Eliminate the resistance of M sub C out of the beam by putting the hinge. Okay, hinge. You can have a hinge at your door, and then you apply the M sub C into this. It's kind you open the door, this gonna move here, and then this portion gonna rotate about this point, and then you get this, and also this one gonna rotate about this point, you get this. First, change the point C to be internal hinge. Remove capacity of resisting the bending moment, or eliminate the moment resistance out of point C. And then it's going to be the hinge. Okay, and put the M sub C on this hinge. It's going to move to AB over L. So this one going to be AB over L. And then you have the shape Okay, and then you also have 1 unit rotation there. Okay, come up to some example in order you to get used to with the Musler-based law principle. We will use this principle many times in our study. Okay, we're going to draw many things. One is the reaction R sub B, R sub C, and V sub BL, or on the left of B, V sub BR, that's on the right of the B, and V sub D is here, and M sub D also, and also M sub B. Okay, let's start by the inference line diagram of the reaction at B. Okay, and let me illustrate this first. What we have is what we're going to mark C is the same. We release or we eliminate the ability of this pin in resisting of R sub B. So this pin support will change to this roller support that have ability to resist only the force in the x direction. And then we apply the R sub B into it. And then this one gonna move for 1.0 unit. When this one move, it's going to move the beam, going to move like this. Okay. And now you get the inference line. C the same. B just change, okay, and apply the R sub B to move 1 unit. Have the shape like this. And since you know this is 1 unit, right? And over here is going to be what? Over here is going to be 16. And this is going to Y, okay, or the length is going to be 20, so this is going to be 20. We can determine Y by similar triangle, Y over what? This one, 20, Y over 20 equal to, yes, 1 over 16. So Y is going to be 20 over 16, that's it, 5 over 4. That's it's going to be here. Okay, 5 over 4. Next, for the R sub C. Okay, for the R sub C, the B going to be the same. This is going to be the same. We release this. Since this one is the roller, when we release this, we just take it out and put R sub C into it and move this one for 1.0 unit. And then the whole A, B, C gonna rotate like this. And then we have this one for 1. And then this one for 16. Form similar triangle, 1 over 16. And then you have this for Y. And then divided by this one 4 equal to Y over 4. So Y equal to 4 over 16 is going to be 1, 4. But this one is in the lower part, so it's negative 1 over 4. Okay, and you have this. You got what? The B is going to be the same. And then you release the roller at C, put the force, push it to 1 unit. Okay, and then you have the shape like this. You have similar triangle. You get this. Okay, V sub BL. Okay, V sub BL. On the V sub BL, the C gonna be the same. The B also be the same. Okay, but now we're going to draw the roller here. It's gonna be on the left, right? On the left, and put the roller here to eliminate the ability to resist the V sub C, and then we put the V sub C plus on the left is going to be downwards. That is plus V sub C. On the right, okay, it's going to be upward. See, since this force acts, okay, very small, very close to the pin B, and this one is fixed, okay, between point B and point C, and this beam is the rigid beam. This is going to be the rigid beam, and when you mark or fix between two ends, what happens is this is rigid beam, okay, and if you mark here and mark here, what happens when you put the force on this point? There is no deformation, okay, and also no movement. They're still there, okay, because they have 2 points of support. Then this one gonna be in the horizontal direction, and this one gonna move to here with the parallel with this BC, and you're gonna get this one for -1. Okay, it's kind of a little bit hard to understand, but I like you guys to think about it slowly. C there, B there, okay, it's just a little bit on the left of the B, and then you put the roller, and then you put the V, okay, in this side the element can move, on this side the BC won't move, so by in parallel, this thing gonna be in parallel, and it's gonna be -1. Okay, ถัดไป sorry, the next B sub R. On the B sub R, okay, we also have the C, same as before, mark here, and this one also mark here, but this time your beam gonna be a little bit cut out from the B on the left hand side, okay, and this one you may draw it like this one you made it. Then you have the slot here and the slot here, okay, and you push this one by the V sub C down, and this one up by the V sub C, and this one gonna move here, okay, since this one move nothing, it can rotate but it would move, okay, but this one support to move 1 unit, and then we have this, okay, and since this one is the in highlight like this, so this one gonna be in parallel to this, so we have the shape of this of what of like this. Okay, let's put the pin at B and the roller at C, and the force here going to be upward, and put it up, and the force here going to be downward, okay, and going to rotate this. Since this one is 0, so the total of this is 1, and this is going to be in parallel, and then you get this one by using similar triangle as before. This is 1, this is 16, so you have 1/16, and this y, this is 4, so you have equal to y divided by 4, so y equal to 4/16, so it's going to be 1.4, and this one going to be negative, okay, I should correct this a little bit, this is going to be negative. And then we have the moment, okay, we have the moment of M. Oh, we still have V sub D, sorry, V sub D, okay, we going to put B going to be the pin, C going to be the roller, just put this roller guide here, and on the left downward by v sub c, on the right upward by v sub c. And by doing this, you get what? You get this one going to be downward. Okay, it's going to be downward like this. And since this one downwards like this, the free or cantilever part going to be overhanging part also going to move like this. And this is going to be minus a over L. This is going to be a. Okay, this is going to be b. So L is going to be 16. So minus 4 over the length of 16. So it's minus 1 over 4. On this side, it's just move, okay, with b over L. B is 12. That is 12 over 16. So it's going to be 3 over 4. So this one going to move up like this. And we have the line like this. And the summation here is 1.0, and these two lines are in parallel. Okay, we have this. B and C the same. Just cut at D. On the left, move. On the left is the blue, move down. On the right is the red. Move up with B over L. This one with minus A over L. And then you get the shape of this by summation, of the distance here gonna be 1. And these two gonna be in parallel. And this one is again 1 over 4. And this is positive. Yeah, right. This is positive because it's moved up. And previously, if you recall, I did some mistake on this. No, it's going to be plus. Sorry, let me correct this. It's up, it's plus. Okay, and then for the M sub D, the B and C still the same. It's just rotating point. And then what we do is we put the hinge into point D. And then we put the moment over there also. Okay, let me put this one. So put the hinge into it. Okay, and then apply the moment up here. It's move to here with this one for AB over L. It's going to be, this is A, this is B, this is, L is going to be only this. This is going to be 16 meter L. So we have 4 times 12 divided by 16. Okay, and then when we move this, what happened is the line here going to be this, and the line here is going to be like this, and this one is going to be cut 4, and this 3. Okay, and the angle between this going to be 1. So we have this in the form of take C and B the same. Put the hinge at D. Put the moments apply at this point. Move it for AB over L. Move everything for 3. And then the new shape of this is going to be like this. And since you know this is 3, you may find this y. So by similar angle, y over this of 4 equal to, this is 3 and this is going to be 4. Okay, 4 equal to 4, y equal to minus 3. Okay, we have one radian rotation here, and this is going to be the proof of that. You can do it easily. And the last one is the moment at B. Okay, and what happened is the C is going to be the same thing. The A is going to be the same thing. Okay, but you got to put the hinge into that position. Put the hinge into here. Or if you made out this one, you made out this, it's going to be point B, point C, and since the support is going to be here and here, and it's a free end, you just put this hinge into this point. This is going to be the hinge. Okay, and then you put the moment on this part, the moment on this part, and you may see this one have the support on the left and on the right, and this is the rigid beam, no deformation and no movement. When this one no movement, so only the part on the left gonna move. It's gonna move for 1.0 unit radian rotation. So you got this at the shape of the inference line of m sub b. And since this is 4 and this one, so this one gonna be minus 4. Okay, you've got this, and then you put the hinge into the top of the pot B, and then you put the moment, you get the shape of this of minus 4. Okay, and that is another example. That's we are going to consider the beam, but this beam is going to be a different one from the previous one. The first one we have simple beam. The next one we have simple beam with an overhang. But this beam we gonna have statically determinate beam. Okay, we have B here is what is fixed. We have the pin here. If we consider the whole free body diagram, we're going to have 4 unknown. We could have 4 unknown. 4 unknown of what? 4 unknown. 4 unknown. 4 unknown. Okay, so we got to separate this by hinge C. Okay, if we have hinge C, okay, we will have a total of 4 plus 2 equal to 6 unknown. And since we have 2 parts AC and CB, so we have 3 equation times 2 parts, so we have 6. So this is statically determinate beam. Okay, and we're going to determine the inference line diagram of R sub A, of shear V sub D, V sub E, and also the bending moment of M sub D and M sub E. Okay, this is E, this D, this is E. Let's start doing this. The Musler-Betz law can apply to any statically determinate beam easily. And then if we start inference line of R sub A, what we do is we release the force of R sub A by doing this. Just release. Okay, and then put the R sub A here. and move this one for 1.0. The problem is the portion of this beam is going to be fixed at B. Okay, and the beam is rigid. The beam is rigid. Okay, and what happened is we have the hinge here, so this portion of the beam no movement at all, so only this portion gonna move. We're going to have the inference line diagram of this beam like this. Okay, let's see. The B is fixed, the C is pinned. We release the roller at A, put R sub A, move point A 1 unit, and this portion fixed won't move. So we have the shape of the inference line diagram of reaction R sub A like this. Next, the shear V sub D. V sub D, we have this is the same. Okay, this is going to be the same roller. This fix is going to be the same. This is going to be the same. Okay, and let me also say this is going to be fixed to point B. What we have is we put the roller guide to point D. Move this one downward, move this one upward, and then you get this downward. Since this one is the pin, so it's going to rotate like this. So this one is going to be minus A over L. So it's going to be minus A over 2L. Okay, 2L, sorry, A over 2A, A over 2A. And then we have this for minus 0.5. On the top, it's going to be plus B over L. So it's the same. It's going to be A divided by the whole this is going to be A plus A is equal to A. So it's going to be plus 0.5. That is going to be inference line of shear force V sub D. We have the fix at B. We have the roller at, here the hinge at C and roller at A. We put the force downward on the left, upward to the right, and use the minus A over L for the blue here. We get this. And B over L for the red here, we get this. And the shape of the inference line going to be this. And the summation of all this side and this side going to be 1. And this one going to be in parallel. Okay. And that's all for the inference line diagram of the shear force as point D. And next, we have the shear force as point E. This time, let me have this one. Okay, we're going to put what? Put the V sub E. Put the roller here. Eliminate the resistance to V sub E out. And then this is going to be the rigid portion of the beam. Okay, because it's fixed here. And when you apply the force, this is downward, this is upward, in which this is still hinge and this is still roller. What happened is this is rigid. Okay, again there is no movement. That is going to be the same. When it's be in horizontal, what happened is this one going to be moved, and in the horizontal with the downwards of 1.0. Okay, and since this one is the hinge, it can move. When this one move, this portion can move, follow the shape of EC. Okay, and then we have this one as the inference line of V sub E. Again, B is fixed. Okay, and then we have the hinge as C and roller at A. Okay, hinge can move. Okay, can rotate freely, and we put the force downward to the left and upward to the right. But this force produces no effect at all due to the rigid beam to the rigid support. So only on the left of point E, on the left of point E move. When it move, it's gonna move in parallel to this. Okay, and going to have -1 value. And then you connect the rest of the beam, you get the inference line of V sub E. Okay, M sub D. Okay, M sub D. M sub D. To do this, it's going to be the same. Same what? This portion of the beam gonna connect to this, and then you have what? You have the pin at C and roller at A, and then what? You got to eliminate the resistance of the moment at point D by putting the hinge. Okay, this is another hinge to eliminate resistance to M sub D. Resistance to M sub D. Okay, and then you put what? M sub D into that hinge. Okay, you put this one M sub D. So this one gonna move. This one gonna move upward to this. How much it's move? It's gonna move A B over L. So it's gonna move A. This is A. This is B equal to A times A, and L gonna be, this one is gonna be 2A divided by 2A. So A cut A. This is gonna be A over 2. Okay, and then you may what? You may connect. That is going to be the inference line diagram of the moment at D. So the B is lock, the C is the hinge, the A is the pin, and put another hinge into the E. This is another hinge, and then apply the moment is moved for AB over L, and then the shape of the line we have is the bending moment at M sub D. Okay, and the relative angle here is 1. Then M sub E, again M sub E, when you have M sub E, this portion gonna fix to support beam, and then this is gonna be the same hinge as C. This is gonna be pin. Okay, and what we have is to draw the inference line of M sub E. We put the hinge at E to eliminate the resisting to M sub E. Okay, and since this is rigid, again no movement, so this is nothing change. Then the M sub E, okay, gonna rotate this one for 1 unit. If this one gonna move for 1 unit, this one gonna be something like this. It's gonna be A, right? This is A. This is gonna be minus A. So the shape of the inference line here is gonna be like this. Okay, we move it like this. B is the fix. Okay, C hinge, A pin, and we put additional hinge to E to eliminate the resistance to M sub E. We put the M sub E into it. Okay, and then the M sub B, M sub E here produce nothing, only M sub E here gonna rotate this element. It's gonna rotate this element, and since this one is A, this is 1, this is minus A, you got this. Okay, and minus A, you get this. Okay, that is the end of the first part of the lecture on the chapter 4 inference line diagram of statically determinate structure. And the knowledge of this is used to draw the inference line diagram for the reaction, for the shear, for the moment at a given point. And then we will use this diagram to find the loading pattern, which is going to be the next clips, and it's going to be the second learning objective. And after we find the loading pattern, we can determine the reaction at that given point, or the shear force, or the moment. And then later we will use the free body diagram and equation of equilibrium to draw the shear diagram, to draw the moment diagram. So the next clip we will use the inference line diagram to find the loading pattern and to draw the shear diagram and bending moment diagram. Okay, this is end of this clip.